Well, first of all, thank you very much for the invitation. Fun fact, this invitation was the result of a tweet thread that I wrote and Chase happened to notice, and that was great. Maybe that's where publications will move in the future. So today, first of all, hi, I'm Ankit Barik. I'm a postdoc at Johns Hopkins University, and I'm part of the MagPi group, which is the Magnetism and Planetary Interiors group with Sabine and Stanley. And today we'll talk about a Python package or library that I wrote to visualize planetary magnetic fields. Now, at a glance, what this package does is it has a very easy script that you can just run and say, I want to see how the magnetic field of Jupiter looks like, for example. And it will just show you that, but it can do a lot more. But before I get into the details, let me tell you a bit about which planets it deals with. The planets that it deals with is the planets that have an active dynamo. So these are planets that are actively generating their magnetic fields. There are planets, and I have been asked by a few people to also include planets that have sort of remnant crustal magnetic field frozen in their crust, like Mars and the Moon. So I will probably include those in future as well, but right now they include only these planets with the green check mark. And the one that is not shown here, which is Ganymede, which is one of the Galilean moons of Jupiter, which also generates its own magnetic field and is the only moon known to do so. And let me tell you a bit of backstory for this package as to why I decided to write this. So a couple of years ago or so, Sabina, my boss, she was teaching a course on planetary interiors, and I was supposed to go and give a lecture on planetary magnetic fields and how dynamos work and so on. So the first thing I wanted to show the students was how the magnetic fields of planets look like. So I started looking for a code that will generate these figures easily, and I found there were none. I found a lot of publications that have all these figures, but none of them have really given a source code to generate these, nor have they provided a sort of central repository for all the data in a usable way. So I had to go and hunt down all the individual papers where these data were taken from, copy those tables, which unfortunately for the older papers, there were no digital tables. So I had to literally like look at the numbers and type them out. And then I had to slowly write down scripts for each planet and generate these figures for the class. So then about a year goes by or so, and then one of the grad students in our group, he starts asking me, can I use your scripts because he needed to generate some figures as well. So he said, can I use your scripts? I said, yes, sure. And then the scripts back then looked like that, where each planet had just a separate script in there, a quick and dirty script, and the data in there. So I sent him some scripts. And then he said, why don't you upload this on GitHub? I'm sure other people would want to use it too. And then I said, well, that will require some work. As those of you who you code know that putting something out there on GitHub requires some more work to make it user-friendly. So then at some point I decided to do that. I put all the data together in one place. I wrote the scripts in a nice and accessible way. And then it turned into this repository, which I hope you can see this. So this is the GitHub repository, which is open source and publicly available. And now, of course, there is all the data from different sources is in one place, and there are scripts that can provide the data to you in an easily accessible way. But before I get into the details of that, I want to address a little bit on the coordinate system we use. Is the spherical coordinate system. So If B is the magnetic field, then the three components are the radial component in this way, the co-latitudinal component that goes that way, so theta is from the axis, and then there's the azimuthal component that goes along the longitude. And that's how the planet is rotating, and that's up. And the second thing I want to introduce a bit are Gauss coefficients. So some of you probably already know this, but in a region where there are no sources of current, so where the magnetic field is not being generated, and you basically have an insulating medium. So let's say the mantle, if you consider the Earth, so everything outside the core mantle boundary, so the mantle of the Earth and outer space, the magnetic field can be written as the gradient of a potential. And since we don't have any magnetic monopoles, you can derive that the potential satisfies this equation, the Laplacian of the potential is 0. And that can be solved in a standard way, and solving that gives you that solution. Now, what's important about the solution are two things. One is that you have these coefficients dependent on two indices, L and M. For those familiar with spherical harmonics, these are the exact same indices, L and M of spherical harmonics. And L would go from 1 to a certain L max, however good your data is, and M would go from 0 to L for each different L. And the larger the L, the larger the wavelength, and the smaller the features that you can resolve. And as I will show in a bit, it's very similar to a Fourier series in 1D, where the higher modes you go into, you get smaller and smaller features. And the other thing is the radial dependence, which here RP is the planetary radius and R is just the radial dependence. The radial dependence basically goes as follows. As you get closer and closer to the surface generating the magnetic field, you get more and more complex small scale structures. And as you go farther and farther away, you see sort of the small scale structures decay away pretty fast because they go as power of L+1. And then you start seeing really large scale structures. So to illustrate the first point, let me show you how these different modes look like. And you'll see as the numbers, especially the L value increases, you start getting smaller and smaller scales. And then you can use these individual functions and put them together to represent the total magnetic field. So you basically start with, and some of them represent your very familiar modes. So the G10, once it comes about, shows the dipole. G11 is the equatorial dipole, 20 is the quadrupole, and so on. And then you get octupole. So this one illustrates my first point of the L and M indices. And this one will show how we can take the field at the surface, and because we know how the potential varies, we can go up and down, sort of what is known as downward or upward continuation of the magnetic field. So here I will downward continue the magnetic field down from the surface to the core mantle boundary. And you can see that as it goes down, as we go down and down, the magnetic field gets just more and more complex and small scale. Now, the other thing, the exact opposite thing happens as you move away from the surface. The magnetic field becomes larger and larger scale. And the value goes, and the value of the magnetic field goes down as well. And in the other case, the magnetic field intensifies as you get closer and closer to the source region. All this was done to illustrate basically what Gauss coefficients are and how we can upward and downward continue magnetic field, which I will be using quite a bit later. So then I went back to these data sources and I looked up tables that look like this and then copied them all into separate separate data tables. and they're all available in basically .dat ASCII format on in the repository. But what the repository does now is it provides this class called the planet class, where you can call upon a planet and create an instance of this class. And then this gives you basically a very easy way of accessing these Gauss coefficients. Instead of having to look up the table and try to rearrange it yourself as you want, you can simply get the values using the index. So once you've created the class P, you can say p.glm, and that index will just give you these values. So that, for example, gives you the G20, that gives you an H42, and so on. Now, what I will do is do a live demo of the package. People usually avoid that, and we'll find out if the reason is valid. All right, so I hope you can see my terminal screen. So this is how the repository looks like. You have this simple script called MagField, and then you have a module called planetMagFields. So you can use this script for very quick plotting. You can say, I want, as I said, I already showed Jupiter. Let me show Earth, for example. So it gives you some details about the planet and the Lmax to which we know the data and the dipole tilt. And then it gives you the field. Something more you can do is you can say, I want the field. And this one only gives you the radial field, which is what people usually want to visualize. Let's say I want it at the core mantle boundary. So 0.54 in terms of the surface radius is where the core mantle boundary is. So I say that, and it gives me the field at the core mantle boundary. Something more you can do is you can specify a projection. By default, this is using the mole-wide map projection, but let's say I want Mercator. And you get that. Right? This is the familiar world map that we often look at. And we can do this for other planets as well. So this is at 85% of the surface of Jupiter using a Robinson projection. And above all, you can also plot all the planets together using the exact same way. Let's say 90% of the surface for all planets, using also a Robinson projection. This will give you some information about what's the dipole angle in terms of latitude and longitude, or rather co-latitude and longitude. And there you go. You have all the planetary fields at the same place at 90% of surface. So that's what this script does, which is just a quick and easy way of getting figures. The next thing is to show what the module can do. So let's see. So let's say I create a planet class and I want to look at Earth. So I create a planet class by the name Earth. And then I can just access, as I showed, the, let's say I want to look at the G10 Gauss coefficient, which is the dipole. And that gives me the dipole in microteslas. I'm sorry, that's in nanoteslas. I should get my units right. And so on. And you can get the quadrupole and yeah. Further, I can say just plot, and it will just plot the surface field. And then I can further say, if if you look at the call signature, I can specify a radius. So I can say I want to look at 60% of the surface radius, and it has the usual stuff you might need. You can change the color map, the projection, the number of control levels, and so on. Not just that, it can also do something called, it can also filter plots based on the spherical harmonics you want. So let's say I want to, let me just copy that. Now let's say I want to filter it at 85% of the radius, and I only want to keep the L's, so 1, 3, 4, and 5, and M's 4 and 5, and see how does the field look like. So that's how the field looks like if you filter it out. And you can even provide a minimum and maximum for the L and M if you don't want to provide an array. For example, let me show the case of Saturn. And here I'm plotting the field at 75% of the radius with a minimum L of 4. So it will show you L greater than or equal to 4 and all M's. Well, there's only M equals 0 for Saturn. And then you can see the small scale features in the field come up very well. So if you remove everything till the octopole, you get these nice stripy bands of Saturn, which are already well documented. So what else can it do? The next thing it can do is if you like 3D visualization like I do, and if you want to produce files that can be visualized by a visualization software like ParaView, there is the write VTS file option. So let's say I want to visualize Jupiter. So I create the planet class, Jupiter, and under this I have the function write VTS file. And so I set potential extrapolation equals true. So this will extrapolate the potential and compute all the different components, not just the radial one, out to twice the surface radius. And I'm going to use 32 basically radial levels in between. And once I do that, it extrapolates the field and produces, it will write a VTS file, which can then read easily by ParaView. So I have that open already here. So can you see the 3D rendering? Okay. So for example, I basically created a file earlier and used that for rendering this. And you can see clearly Jupiter's really high North Pole, close to the north, and what is known as the great blue spot of Jupiter right here in 3D. And if you play around it a bit more, you can also produce renderings like the one I have in my background, which is of Uranus. Lastly, since this part already does the potential extrapolation, there's also a potential extrapolation routine separately, which is called extrapot. So what that does is it takes the Lmax of from the planet. So this is 1, is this surface radius is set to 1, it's all normalized there. Then it takes the radial field at that surface and takes an array called rout, which you have to create. So I go from the surface to twice the surface, 32 radial levels. And then I go, and then it just extrapolates the field. And then you have access to these arrays, basically 32 radial levels, and then 256 points in longitude and 128 in colatitude. And then you can just use that data to plot at any field, at any level you want. All right. So I think I've covered more or less all the capabilities of the. Oh, lastly, yes, very important thing to people studying planetary magnetic fields is spectrum. So people love looking at the energy spectrum of magnetic fields. So while producing this package, I was using the data to produce some spectra for my work repeatedly, and then I thought, why don't I just make it part of the package? And so let's say I want to look at, you can see it clearly like Jupiter, and then spec would just produce what is known as the lowest spectrum, which shows the energy at each L in the radial magnetic field in nanotesla squared. So you can see how the energy spectrum looks like. And not just that, it also takes in a radius. So you can actually provide it, what does the spectrum look like at 80% radius. And then you can see, as I was saying, the small scales gain energy as you go down. And you can see that clearly happening here. I'll just show another example for Earth. And that's how the Earth's surface magnetic spectrum looks like. And this is what it looks like right at the core mantle boundary. This was, in fact, one of the first ways in which how people tried to infer where the core mantle, or at least one of the ways in which people try to infer where the core mantle boundary might be, by seeing where do these sort of scales, all these scales come to the same energy level, comparable energy level. And it seemed to work. So I think I've covered more or less all that this can do. Now I'll just mention that the libraries you need for, if you don't want to do anything very fancy and just use simple visualization, these are the only things you would need: NumPy, Matplotlib, and SciPy, which if you're working in data visualization in any capacity, you usually have it installed. If you want, so the package internally has a hammer map projection coded in. But if you want any other projections like Mollweider, Robinson, or Mercator, etc., you would have to use the CartoPy library. And the package is set up such that you can just provide any of the names from this list on CartoPy's webpage, and it can take it and use that as a projection. For potential extrapolation, you would need what is known as the SHTNS library, which is Nathaniel Schaeffer's spherical harmonic transform library. So that's what it uses for extrapolating potential and computing all different magnetic field components. And finally, to write the VTS file that I just produced and used for 3D rendering, you would need the PyEVDK library. But even without all of these, you can still use the package just to produce visualizations at different radial levels and so on with a hammer projection in a simple way. I want to thank our grad student, Raghupati, who sort of persuaded me to push this all up on GitHub. And I want to thank John Arnaud from UCLA and Thomas Augustin from IPGP Paris for testing it and then suggesting different features and also fixes. And my next plans are to include also planetary bodies like Mars and the Moon with remnant crustal magnetization, and also to provide an option for an out-of-the-box 3D plotting with Maya V. So you can just say you don't have to even go to ParaView to produce a 3D rendering. You can just, from your IPython terminal, you can just ask for a 3D view and it will give you that. And that's more or less what I had to say. I hope you can download the package and have a look around and play with it. And it's useful for for teaching and/or research. And please send me, I would appreciate any feedback, and you can get in touch with me via email or following me on Twitter. And I'm happy to answer any questions here.